Hi, today we start the beta and gamma function. In this video, we will talk about the only beta function. Later on, we will discuss about the gamma function. So, when we talk about the combinedly beta and gamma function, the beta and gamma function also called Euler's integral, and these are the improper integrals. The beta and gamma functions are extremely useful in the evaluation of integrals. So that's why we study the beta and gamma function. It is helpful to integrate such function which we sometimes cannot integrate directly, but with the help of beta and gamma function we can integrate. So it is useful in the integration. Now we talk about the beta function. The beta function that is defined denoted by beta mn, or sometimes we write bmn, that is defined in the form of integral. Beta mn is equals to 0 to 1 x to the power m minus 1 1 minus x to the power n minus 1 dx, where m and n both are non-zero number which is greater than 0. So for example, we say if we have the integration 0 to 1 x to the power 1 by 2 1 minus x to the power 4 dx, directly we can write this will equals to beta 3 by 2 and 5. Here m minus 1 is 1 by 2, that's why m is 3 by 2, and n minus 1 is 4, that's why n is 5. Similarly, if we write 0 to 1 x to the power 1 by 2 1 minus x to the power minus 3 dx, this is not a beta function because here n is minus 2, which is negative, but as I told you, n should be the non-negative, non-zero and non-negative. It is a positive number. Simply it is positive number. M and n is positive. So next we talk about the properties of the beta function. The first property we have, beta mn is equals to beta nm. How we prove this? We have beta mn is equals to 0 to 1 x to the power m minus 1 1 minus x to the power n minus 1 dx. This is the formula of beta function. So what we do here, we put x is equals to 1 minus x. So what we get, 1 minus x to the power m minus 1 and 1 minus x power n minus 1 dx. Here we have used the property 0 to a fx dx is equals to 0 to a f of a minus x dx. That property of the definite integral we have used here. So what we get finally, 0 to 1 x to the power n minus 1 1 minus x to the power m minus 1 dx. Thus we get it is a beta nm. Hence beta mn is equals to beta nm. Thus we prove the first property of the beta function. Next we have beta mn is equals to 2 into integration 0 to pi by 2 sine 2m minus 1 theta cos 2n minus 1 theta d theta. So what we do now, according to the definition of beta function, we have beta mn. Now we put here x is equals to sine square theta. So what we get, dx is equals to 2 sine theta cos theta. Here x tends to 0, as then x tends to 0, then theta tends to 0. As x tends to 1, then theta tends to pi by 2. So the limit from 0 to 1, it will be 0 to pi by 2. We substitute all the values here, and the beta function will be 0 to pi by 2 sine square theta m minus 1 1 minus sine square theta n minus 1 2 sine theta cos theta d theta. After simplifying this, we get our desired result. It is 2 times integration 0 to pi by 2 sine 2m minus 1 theta cos 2n minus 1 theta d theta. Thus we prove the second property of the beta function. Now let's talk about the third property of the beta function. Beta mn is equals to m minus 1 factorial n minus 1 factorial upon m plus n minus 1 factorial. This property we have to remember when we study the gamma function, when we have the relation between beta and gamma function. Let beta mn is equals to 0 to 1 x to the power m minus 1 1 minus x to the power n minus 1 dx. m and n are positive number from the definition we have. So now we integrate by part. We get beta mn is equals to x to the power n minus 1, 1 minus x to the power n upon n minus 1. We take the limit 0 to 1 and minus that you can verify from the integration of by part. Minus 0 to 1 m minus n x to the power m minus 2 and 1 minus x to the power n upon n minus 1 dx. Here we get from the first part of the integral, that will be 0, and from the second part we get m minus 1 upon n, that we take outside. 0 to 1 x to the power m minus 2, 1 minus x to the power n dx. Here thus we get m minus 1 upon n beta m minus 1 n plus 1. Next is, similarly we can have beta m minus 1 n plus 1, that will equals to m minus 2 upon n plus 1 beta m minus 2 n plus 2. Students are required to, it is suggested they can verify this result. Similarly we have beta 2 m plus n minus 2 is equals to m minus 2 upon n plus 1 beta 1 m plus n minus 1. Now we multiply the preceding equations. We get beta mn is equals to m minus 1 m minus 2 up to 2 1 n plus 1 n plus 2 up to m plus n minus 2 into beta 1 m plus n minus 1. Now we multiply in the numerator and denominator by 1 into 2 into 3 up to n minus 1, and the second part that we define according to the definition of beta function. So what we get finally, m minus 1 factorial n minus 1 factorial upon m plus n minus 2 factorial into integration 0 to 1 1 minus x m plus n minus 2 dx. This is the simple integration that we have. What we get, the integration 1 minus x power m plus n minus 1 upon m plus n minus 1 into minus 1. When we put the limit at 1 it will be 0, at 0 it will be like that, m minus 1 factorial n minus 1 factorial upon m plus n minus 2 factorial into 1 upon m plus n minus 1. So beta mn is equals to m plus 1 m minus 1 factorial into n minus 1 factorial m plus n minus 1 factorial. This we get the result what we have proposed in property 3. Next is, here we have the two property beta mn is equals to 0 to infinity x to the power m minus 1 1 plus x power m minus m plus n. So again we start with the definition of the beta function that we have. Now we substitute here x is equals to t upon 1 plus t. What we get, dx is equals to 1 upon 1 plus t square 1 upon 1 plus t whole square dt. Now what we talk about the limit as t is equals to 0 at x is equals to 0 and t tends to infinity as x tends to 1. Then the expression of beta function that is reduced in the form of, after putting the value of x is equals to 1, x is equals to t upon 1 plus t, this we get. From here, after simplifying, we get beta mn is equals to 0 to integration 0 to infinity t to the power m minus 1 upon 1 plus t m plus n dt. By replacing t is equals to x, we get 0 to infinity integration x to the power m minus 1 1 plus x power m minus m plus n dx. Similarly, since beta mn is equals to beta nm, we have 0 to infinity x to the power n minus 1 1 plus x to the power m plus n dt. Thus we prove the first part here. Now we use this result to prove the second part. Now For the second part, what we have, beta mn is equals to 0 to infinity x to the power m minus 1, 1 plus x power m plus n dx. So now what we do here, we split the interval 0 to infinity into two parts, 0 to 1 and 1 to infinity, like I1 plus I2. Now we substitute x is equals to 1 upon t in I2, so that we get dx is equals to minus 1 upon t square dt. Now what about the limit? T is equals to 1 at x is equals to 1 and t is equals to 0 at x is equals to 0 we get. So now we substitute these values here, so the limit is 1 to 0. That we change here, minus 1 upon t square dt is there, so that minus comes on that side, and the interval change here 0 to 1. Finally what we get, t to the power n minus 1, 1 plus t power m plus n dt. Now we replace t by x, again we get 0 to 1 x to the power n minus 1, 1 plus x power m plus n dx. Thus I1 plus I2 is what? 0 to 1 x to the power m minus 1, 1 plus x power m plus n dx, plus that is I2 0 to 1 x to the power n minus 1, 1 plus x m plus n dx. Thus we prove here the second part, beta mn is equals to 0 to 1 x to the power m minus 1 plus x to the power n minus 1 upon 1 plus x m plus n. Thus we prove the second part of the property 4. Now let's see one example of the beta function. Here we have to show that the integration limit from 0 to a x to the power m minus 1 a minus x to the power n minus 1 dx is equals to a power m plus n minus 1 beta mn. So we start with the LHS. LHS is given, that is integration 0 to a x to the power m minus 1 a minus x power n minus 1 dx, like. So what we do here, we put here x is equals to ay in LHS. We get 0 to 1 ay power m minus 1 a minus ay power n minus 1 into a dy. When we put x is equals to ay, so that we get dx is equals to a dy. So in the place of dx we have written here a dy. Now we eliminate a from all these factors. What we get, a to the power m minus 1 plus n minus 1 plus 1, and the terms in the y to the power m minus 1, 1 minus y power n minus 1 dy. Now we eliminate the a power m plus n minus 1 from outside the integral. That is the simple beta function we left here now. That equals to a to the power m plus n minus 1 beta mn. Thus LHS is equals to RHS, we prove. Let's take another example. We have to show that beta m plus 1 n upon beta mn is equals to m upon m plus n. We will solve this problem in a little bit different way. We take here beta is equals to beta m plus 1 n is equals to 0 to integration 0 to 1 x to the power m 1 minus x to the power n minus 1 dx. So we can write it in another way, 0 to 1 1 minus x to the power m x to the power n minus 1 by taking the property beta mn is equal to beta nm. Now we integrate it by part. Integration by part we use here. So it is 1 minus x power m x to the power n upon n, limit is 0 to 1. That will be the 0 when we put the limit. And now next, minus integration 0 to 1 m 1 minus x power m minus 1 minus 1 x to the power n upon n dx. So here minus 1 and the minus sign of the integration, that makes the minus minus plus here. So finally we get what? M upon n integration 0 to 1 x to the power n minus 1 into x 1 minus x to the power m minus 1 dx. Now we put here m upon n integration 0 to 1 x to the power n minus 1, and in the place of x we take here 1 minus x into 1 minus x power m minus 1 dx. Here m upon n 0 to 1 x to the power n minus 1 1 minus x to the power m minus 1 dx minus 0 to 1 x to the power n minus 1 1 minus x to the power m dx. Thus we have the two different beta function now. It is m by n beta nm minus beta n m plus 1. So what we get, m by n beta mn minus m by n beta m plus 1n. Thus 1 plus m by n beta m plus 1 n is equals to m by n beta mn. When we equate with the LHS and RHS that we have taken, in this way we get n plus m beta m plus 1 n is equals to m beta mn, and finally we get beta m plus 1 n upon beta nm is equals to m upon m plus n. Thus we prove the property. This property we will use in the integration as well if required. So beta m plus 1 n upon beta nm is equals to m upon m plus n. Now come to the next example. We have to prove that (0 to pi by 2) sine m theta cos n theta d theta is equals to 1 by 2 beta m plus 1 upon 2 n plus 1 upon 2, where m and n both are greater than minus 1. This example you can also find in the reduction formula also. You can solve using the reduction formula. Here we use the beta function. We have the beta function 0 to pi by 2 sine m theta cos n theta d theta, that equals to 0 to pi by 2 sine m minus 1 theta cos n minus 1 theta d theta sine theta cos theta d theta. We split sine m theta in the form of sine m minus 1 theta into sine theta, and cos n is equals to cos n minus 1 n cos theta. That will equals to 0 to pi by 2 sine m minus 1 theta 1 minus sine square theta power n minus 1 upon 2 sine theta cos theta d theta. Now we substitute here sine square theta is equals to x, so that 2 sine theta cos theta d theta is equals to dx. By differentiating it we get 2 sine theta cos theta d theta, that equals to dx. Thus we get now see the next example. So that beta mn is equals to beta m plus 1n plus beta m n plus 1. Now by definition from the RHS we have beta m plus 1n plus beta m n plus 1. That we write from the definition of beta function, integration 0 to 1 x to the power m 1 minus x to the power n minus 1 dx plus 0 to 1 x to the power m minus 1 1 minus x to the power n dx. That equals to 0 to 1 we put here x to the power m minus 1 and 1 minus x to the power n minus 1. That we take common from the both, so that we get here x plus 1 minus x dx. So x and x cancel each other. Finally what we get, 0 to 1 x to the power m minus 1 1 minus x to the power n minus 1 dx. That is simple beta mn from the definition of beta function. Now we see the next example. We have to express integration 0 to infinity x to the power m minus 1 upon a plus bx power m plus n, where m, n, a and b all are positive numbers. We have to show this integral in term of beta function. So what we do here, we put bx is equals to ay, so that dx is equals to a upon b dy. Now we put these values in the given integral. As we know, here the limit will not change as the limit is 0 to infinity, so that what we get after putting these values, 0 to infinity x to the power m minus 1 a plus b x power m plus n, that equals to 0 to infinity ay upon b power m minus 1 a plus ay power m plus n into a upon b dy. So finally what we get, 1 upon a to the power n b to the power n will be outside of the integral, and 0 to infinity y to the power m minus 1 1 plus y to the power m plus 1 dy. And as we have proved about the property of beta function, that will equals to 1 upon a to the power m b to the power m beta mn, a to the power n beta to b to the power m beta mn. Thus we have shown this integral in the form of beta function. Next example we have, so that beta m 1 by 2 is equals to 2 to the power 2m minus 1 beta mn. Again we use the property of beta function. Here these examples we are solving using the property of beta function. So what about the beta mn? Here n is 1 by 2, that is 2 integration 0 to pi by 2 sine 2m minus 1 theta cos 2n minus 1 theta d theta. So by putting n is equals to 1 by 2, we have beta m 1 by 2 is equals to 2 into integration 0 to pi by 2 sine 2m minus 1 theta d theta. By putting n is equals to 1 by 2, that is the cos 0 theta, that will 1. Now we put n is equals to m, we have beta m m, that 2 into integration 0 to pi by 2 sine 2m minus 1 theta cos 2m minus 1 theta d theta, that equals to 2 into 0 to pi by 2 sine theta cos theta power 2m minus 1 d theta. This will equals to 2 times integration 0 to pi by 2 1 by 2 sine 2 theta 2m minus 1 d theta. Thus we get here 1 upon 2 to the power 2m minus 1 into 2 0 to pi by 2 sine 2m minus 1 2 theta d theta. Now we put here phi is equals to 2 theta, so the limit will be 0 to pi, that we get, and thus we using the property of beta function, this is 1 upon 2 to the power 2m minus 1 beta m 1 by 2, and so beta m 1 by 2 is equals to 2 to the power 2m minus 1 beta m n. Thank you for your concentration. If you have any question, definitely comment on the comment box. In next video we will see about the gamma function and the relation between beta and gamma function. And do not forget to subscribe our channel for further updates. Thank you.